Hello, everybody. Welcome to Ordinary Differential Equations. First of all, to introduce myself, I'm Hasala Karnaratna, Dr. Hasala Karnaratna, and due to long Sri Lankan or lengthy Sri Lankan names, um, you can find me in under two different names, either Hasala Karnaratna, that is my uh, Sri Lankan recognized name, and then Hasalagallalu or Hasalagallalu Kankanamalagi. That is exactly where you can find, how you can find me if you look it up on the web, like if you Google me, or at this point, like I'm at Roger Williams University, and I'm an associate professor of mathematics there, and they are also I'm recognized by the name Hasalagallalu. So uh, either way, uh, we can have that part of the introduction simple because we all know Sri Lankan names, usually are lengthy, and some of us have to suffer through this lengthy name process appeared in a couple of different ways in different places. All right, so let's get to our work. First of all, I'm very excited to be here. First of all, I would like to thank Dr. Prabhat Silva for giving me this opportunity to um, be a part of this excellent work. And especially, I would like to thank again, for the choice of the text also, like, because this was not a course um, on differential equations. Like, it is not just the topic that he came up with. Like, when we had this conversation, he said, let's have ordinary differential equations by using Arnold's book. So let me say something about this, because this whole story, or the entire conversation that we are going to have, will be depending on this context. So first of all, uh, let's look at these two. Let's have this housekeeping stuff easy, so that we can recognize like exactly what we are going to do and how uh, we are going to do in terms of these textbooks. First of all, the primary textbook is going to be Ordinary Differential Equations by V.I. Arnold, right? Um, and the primary text is edition 3. And the interesting part is I do have a secondary textbook for this conversation, and that is none other than just the edition 1 of the same book. This is kind of this is the first time that I'm having this kind of experience too, right? Because usually when we have uh, a textbook and a supplemental textbook, it's going to be like completely something's going to supplement. There should be a significant difference between one and another. But in this case, like, it is just the same author, same title, and two different editions. What's the big deal? And that is exactly the point. And to recognize this, first of all, I would like to invite you to uh, have a quick Google search. First of all, you can you can Google V.I. Arnold. I'm not trying to just get one personality out of this context and say, like, oh, we are going to craft this entire course around the person. No, it is not that, right? So we should know exactly like the background a little bit. That background can provide a lot of information. So if you go ahead and let me show those things, I may have those um, Google search tabs with me. So let me stop sharing this for a moment. Um, Right. So now you can see my screen where I looked up. The first two tabs are exactly about the Zoom session that I'm recording this on. And let me tell you, like, one more thing. Now, in this session, like, this is pre-recorded as an introduction. And in the future, like, I'm willing to have some conversation, like, with some interaction if possible, like, if the timing works out. If not, that's, yet we can work it out in this way. So, the first step, right? If you check who V.A. Arnold is, like, he was a mathematician and and one of the pillars in dynamical systems and ordinary differential equations. So these two directions, like dynamical systems and ordinary differential equations, there are like two different areas. One, like, both of them are having application oriented front, and at the same time highly theoretical end. So Arnold had that work mostly in theoretical end, like, so you can just check, like, one way of checking the profile is like to go to Wikipedia. You can do that. And one very interesting fact that I find is if you go ahead and click on, like, this is something that you should get to know. If you get to know about, like, this web page, or like the mathematical genealogy project, that will provide, that provides the heritage, like, where each academic, like whoever's having a PhD, like where they're coming from, like who's the advisor, who's the advisor of the advisor. For instance, like, if you go to this, and if you click on this, like, this is the advisor of V.A. Arnold, right? So if you click on, this is a well-known character in uh, Colmagnar is a well-known character in dynamical systems, and like many different directions in even in analysis. So here, what I want to point out is this: uh, V.A. Arnold produced 46 PhD students and 244 descendants. That means, like, students of students and students of students of students. That is what you can find here. So it is like, it is not only just an isolated presentation. So um, Arnold is a well-established personality in that um, area of study. So you can find more information. I'm not going to say much. So why do I need to emphasize that to get to this story? Because now, if you check, now I do not know whether you have this book with you already. If you do not have it, like, I recommend you to find it. And there is an easy way of doing that. I do not know the legal grounds of that, though. Um, Here we have, like, if you check ordinary differential equations edition 1 Arnold PDF, right? Simply the PDF. If you search that, there is a free, there's an edition, there's a PDF available for edition 1. The only drawback in this case is if you open it up and if you go ahead, you will see the readability. It is not like really well readable. For some reason, it is not well scanned. So in any ways, it is there. You can find it. And I do have edition 1 of this book with me. Actually, I bought it from Sri Lanka. When I was like, there's a uh, book shop called Expographics. I do not know whether it is there or not. Like, many things could be different. So I bought it from Expographics, I guess, like around 2009 or something, right? It was edition 1. Now, that is exactly the edition that I've seen. And then in preparation to this course, when I checked for a newer edition, I found another one. Of course, there was an edition 2 and then it moved to edition number 3. Now, if you check, if you Google the same thing, ordinary differential equations edition 3 Arnold PDF, this second one, all right, you can check this title. Right, when you click on that, it is giving you the third edition of uh, this book. Now, this is the interesting thing. These two editions are very different from each other. I mean, the first edition of this book, it was just the raw presentation where you can find like exactly uh, the theoretical framework. And then starting from that, it's not going to talk about much about like anything related to solving differential equations, nothing, right? So this kind of a book now, if you try to find this book and if you try to buy the first edition, and if you do not find it, I'm not surprised, because not many people would buy that book except for whoever's whoever is willing to have that deep conceptual understanding and who's going to have that sentimental value of the book. So that is one issue, not an issue. We know how the business would work, like when it comes to textbooks, right? So that is why if you do not find it frequently, that may be the reason, and that is one of the things that's being addressed, that had been addressed in edition 3. They introduced some solution type, so at least like the way that it's going to work. But first of all, when I saw, like, since I saw the first edition at the beginning and then I saw the second edition, the third edition, I felt like, oh no, because the first edition has that abstract value in it, and the third edition, the nice thing about it is it has the same value, but it has something more. So when we read the third edition, now nice thing about this PDF that's available right in front of us is this is very readable. And I highly feel that these available copies, I mean, these are well recognized, and the legal ground should be fine. The reason is like most of these books, like if you try to find them, I mean, even when I try to find it to purchase, even it is, I mean, they're not frequently available. Some of them, like I need to buy a used copy. I mean, I do not see like ongoing printing of some of these books. So this is what I am going to say. I'm saying too many things about the books, but let me tell you the reason. The reason is the edition 1 has the framework. That framework is simple. That framework is simple, but it could have been explained a little further. And that little further explanation happened in edition 3. I did not read edition 2 in between. So if you find it, you can take a look at that too, but I'm not going to do that. In edition 3, I find more elaborative presentation of that theoretical framework. At the same time, it provides like a little bit of that concrete layer of solving differential equations, but I'm not a huge fan of that part of the presentation because I would like to maintain that abstract framework in this conversation, because that is the beauty of this approach, of the approach that Arnold provided in his first edition. So that is what we are going to do. So this is why I gave one comment right here in the lecture. Let me go back to my writing interface. I wish I had a faster way of moving back and forth with this sharing. Unfortunately, it is just the same old way that works. All right. So now look at this. Here I mentioned like these two books, and then I gave a particular comment. Do not read either of these texts until we have a conversation. This was the conversation that I mean the conversation is exactly what we had, what we mentioned a couple of minutes ago. Because if you try to read edition 1, you may feel it is abstract, and you may feel at a certain point like if it was explained a little bit. And if you read uh, edition 3, sorry, if you read edition 3 actually, you will find more elaborative um, version of it. However, it has like other like concrete considerations. But when you consider edition 1, on the other hand, it has the abstract form, right? So I would like to look at the framework from edition 1 and try to map that exactly to edition 3 to work with that abstract version of this conversation. So that is the point. So when you read edition 3, let's try to do it in this way. I will point out exactly where I would be working at, which parts I'm looking at, which parts we are going to have conversations on, which parts we are going to just hand wave and say like, oh, you can in fact read and understand it, right? So we can have that. And that's the plan. So we will have a very close look at it. And at the same time, when we work with this presentation, I mean, when we are gonna, when you're going to have this conversation, I am planning to do this uh, by directly following some of the sections. I will follow, even sometimes I will accept some of the content, some of the parts from the book, and then I will elaborate and I will work with some of the problems, some expansions in certain cases, and like that, right? So, a concise course plan. Let's try to make it like simple. Of course, this is very dense. We cannot have like in 4 or 5 different points, like what we're going to do in this entire conversation. It is like too short. So we will expand each component. And even like when we consider like, let's say overview and introduction, we start it here, right? This lecture or this conversation is exactly the starting point, but it is not going to be uh, over just after this lecture. We are going to continue that conversation because I mean there are certain components that uh, we need to let me see. Oops, right. So we need to maintain in terms of each component, right? So let me give you a quick idea about like these sections also, just an overview. First of all, we will have an overview and introduction where we are going to see what we are going to do, pretty much what we are going to do and how we are going to do. And then in the second part, we will learn phase spaces, phase flows, vector fields, and direction fields. Like we are going to have the layout for this. And in a moment, I'm going to talk to you more about this approach. So you will see I'm not talking about differential equations like in this part 1 or part 2. And then when it comes to part 3, I'm going to talk about basic theorems where we have like when we talk about differential equations, we have a bunch of um theorems where we establish existence, uniqueness, continuous dependence on initial conditions, And then extensions of the solutions, which means like when we find a solution, how can you find the maximal interval where that solution can be defined on? In certain cases, the solutions may not go all the way up to infinity in terms of the time variable because there could be a finite scape. The solution has a singularity, it just explodes. So in either case, in each case, we need to have this um, conditions established. Now, in a conventional differential equations course, there's a frequently asked question like why we are doing this existence uniqueness. So I mean, when we have a differential equation, if we can find a solution, what's a big deal? Like, would this even matter? Now, I will show you exactly the importance of this. We will talk about, like, first of all, we will talk about these results, and then we will talk about the proofs of these results, right? So when it comes to the proofs of these results, what we are doing is basically analysis. So I will show you the entire conversation of ordinary differential equations that we are going to have in this is an extension or uh, a branch of real analysis. I will show you that approach because one thing that you can do is like uh, if you have some computational background. I mean, this is the whole point of like hiding this computational component right at the beginning. If you have a computation, I mean, some of you may already have that background. So you know how to compute a differential equation, I mean, a solution of a given differential equation for a simple case. And you may feel like, oh, what's a big deal? This is like existence. I mean, the solution right there. Look at what I've written down. That's the solution, right? You can say that. But on the other hand, one can, I mean, if one thinks about mathematics as a, uh, let's say, um, in a process of reasoning, so just like a foundation of analysis, like you're constructing the foundation. If that is the case, one can say like, oh, I do have existence and uniqueness, and then you're going to look at a very simple differential equation like, let's say, that you might have seen in many cases, like let's say exponential growth, dy dx equals dy dt equals just y, right? So we have seen that kind of a scenario, and that even if you have seen it in application somewhere else, right? So if you consider that kind of a differential equation, and now if you have existence and uniqueness, I mean existence of a solution, now you can name, let's pretend that we never seen exponential function before. Now you're going to have a point where you can introduce these functions into analysis in a formal way through this approach. So once you guarantee existence, for instance, like let's say, let me give you a brief idea now. You use sine and cosine functions frequently. If you go back and check where you have seen sine and cosine functions right at the beginning, you have seen them in, like, let's say in advanced level somewhere at a certain point, like, or even before that, right? So in seventh, eighth grade somewhere, you have seen, like, let's say a triangle, and then with a triangle, you know the opposite divided by the hypotenuse, and it's going to be sine. You wrote it down, and then in advanced level time, you extended that to the unit circle and say like, oh, that is like the same triangle, it's just extended. Now let me ask you, when you learned analysis, you even treated like continuity limits very carefully with epsilon delta definitions, right? So you did not assume much, right? You did not even assume uh, the construction of, I mean, you did not assume real numbers even. There's a construction, there's a piano, I mean, there's a approach called piano. uh, um, construction to the real numbers, and then there's a Cauchy approach, like where you consider like in terms of completions. There are different versions of like even constructing the real number line where you stand on, right? You start from there, and then you try to uh, formalize exactly the real number line. Now think about this. If that is the case, how can we have that? How can we have that kind of like a sloppy definition for a trigonometric function like triangle and like opposite divided by hypotenuse? Is it gonna? I mean, who has the definition for opposite or hypotenuse? That whole thing is depending on a triangle. So now, uh, without doing that, here, right? So if we prove or if we establish this existence uniqueness to a very simple system, a second order system, we will be able to come up with two functions which would mimic exactly the properties of sine and cosine. And the nice thing is they do have that origin already. The existence is guaranteed by the existence uniqueness. In other words, what I'm saying is we are going to give these theorems, existence, uniqueness, continuous dependence, the extensions and rectification, all of these, like all of these theorems, they are corresponding place. Those are not like some background noise that you're going to have in a differential equations course. It should be exactly the focal point of this entire conversation. The whole thing is revolving around this, like you are going to have that analytical approach to define your entire pathway to talk about solutions of differential equations, but also at the same time existence of some of the functions. You can do that. So there are different entryways into these functions. I mean, I'm not saying like this is the unique way of doing that, because one can define exponentials or like sine or cosine even by using power series approach. That is one way from analysis, but there are certain components where you might need to struggle to establish like simple stuff, right? Sine square plus cosine square equals 1. Think about writing sine and cosine in terms of like two power series and squaring them, adding them up, how it's going to work with like all the cross terms. There could be some stuff, and there could be different approaches where you can see it in a better way. So that is the beauty that we are going to see in this conversation. So sometimes, I mean, not having that, not having the example right at the beginning is the way to have the value to have that example later. So that is exactly what we're trying to do. So why am I elaborating all of these pieces, like all of these components on day 0? The reason is this. Now, when we talk about this abstract conversation, I mean, when we are going to have this abstract conversation, there is a certain point one might feel tired a little bit, like, because theorems proves. Is it going to be the way that we are going to do this? Uh, we need to find a purpose of doing that, right? We need to find why we are doing that. I mean, that is exactly the beauty that you can find in this approach that combines both that theoretical background and at the same time the geometric intuition coming from Arnold's approach. And then when it comes to the next part, like where you can see like linear systems, right? So linear systems are going to be like exactly the higher order, uh, higher degree differential equations combined, I mean like diluted down to first order systems, and then we can talk about those systems. And we can do many things by considering those systems. And sometimes we can talk about like different parameters or different variables interacting with each other to their evolution rates, right? So how can you describe that? The only way, of course, when we have a system, we are going to have linear algebra, right? So we are going to have that approach. And so that's where we are going to have that combination of linear algebra together with story of ordinary differential equations. And then at the same time, don't forget, like even when it comes to existence and uniqueness, we are going to have that entire conversation not only to a single differential equation, we are going to establish that for uh, for a system. So I'm not going to say that all of these parts are going in a linear order, because at a certain point we might need to go back and forth a little bit. The point is, when I prepare these lectures, especially since I mean, this is a course that I'm going to, I mean, I'm offering by using this book for the first time, which is a very, very novel thing. I mean, which is a very cool thing. But at the same time, we are going to work it together. So sometimes if I feel like, oh, I should have mentioned something even like with further elaboration, I'm going to revisit that topic and we will have it. Like the point is to have this entire conversation as a complete, as much as possible, a complete entryway to differential equations. And at the same time, later when you use it somewhere with some differential equations in terms of like application orientation, you're going to still have the theoretical part running inside you. Or on the other hand, if you consider this as an entryway to have like, let's say, a combination or supplement to the analysis component, that's exactly going to be uh, the most valuable way of looking at it. And okay, I forgot. There is a very important third entry point. The third one is there is a different area in mathematics called dynamical systems or dynamical systems. And actually, my work, I do some research on dynamical systems and control theory. Control theory is a subcategory, subpart of um, dynamical systems. So where pretty much like one can just simply say like, oh, it's just the math behind the control system, just robotic systems where you have like, let's say, adaptive cruise control in a car. How do you have that kind of a control system defined? I mean, you can just simply have it. It's an engineering story, but behind that engineering story, there's like heavy mathematical component going around. So that's exactly the part that I'm working on. So if you try to think about like at a certain point an entryway, I mean, control theory is very specific, but when you consider like the dynamical systems, the realm of dynamical systems, that has a wider scope. And what Arnold does in this approach is bringing the elements of dynamical systems to start with the abstract version of differential equations. So in other words, it is just like this. All right, one last thing to go from this lengthy, boring introduction. I apologize because I mean, it seems like I've been talking too much about like what it's going to be. But I guess it's worth. So, um, what Arnold does in this scenario is to bring the dynamical system approach into this whole conversation in a way that you're trying to prepare the dance flow. You're not trying to define dance moves, right? If you learn differential equations like just and application orientation, like to solve this differential equation, to solve this, to solve that differential equation. It is just like you, one step at a time, you try to learn a dancing move, right? But forget about that for a moment. Where are you going to dance if you do not have a flow? So this is about preparing that dance flow. And if you do that with a very good intuition, eventually you might not end up being a dancer. Instead, you will be able to become um, a dance, who's it called? Like a manager who knows exactly how the dance floor works, and he or she knows like exactly how um, it's going to work, right? So you can be just behind, I mean, not behind, like you can be in front, like far ahead of, just like defining these dance moves. So that is kind of like the approach that we are going to have. So that is what we are having at the end, like ODEs in on manifolds. Like that's like, what are manifolds? Like on differentiable manifolds, we will talk about that with less amount as much as possible, like not to have like too overwhelming unknowns into the picture. We will try to just uh, make our path the way from point A to point B, right? As much as possible to get the best weave around. So that is a plan, right? And of course, I cannot do it without your interaction. I mean, because you will provide me the feedback and we're going to do that together. And then in terms of like the housekeeping stuff, I might have covered some of this already. The approach, and of course, we know like we are going to talk about this in terms of like we are going to have these conversations, and then along the way, I will provide like some assignments, interesting problems. Some of them could be even concrete, but I will not provide some concrete examples with like computational aspect. Like it's not going to give us that taste. If I ask you to compute something, I'm going to expect some intuition behind it. Otherwise, like, I mean, the point is you will get this computational background in many other places. And even if not, like if you just read a book, you will be able to get that. I'm pretty sure some of you may have this background with differential equations, maybe a little bit like in terms of like solving differential equations. So what I'm going to do is like not to have that, right? As I mentioned before. And then what else, right? So what else exactly? This is a good question because this is exactly the parts that we have not seen, like the issues we may figure out, like what to do, uh, how to present certain components. I mean, like let's say like the unknown. It's the unknown until we figure it out. So let's have that. And the main goal is to retain this taste of abstract approach to this entire conversation. All right. So that is the important part. Let's keep the main goal in our mind. So at a certain point, if we get a little tired of what we're doing, that's exactly when we should consider mm, to revisit and see what we're doing. And that's going to give us again an energy boost so that we can start with a fresh mindset. So with this, I am going to invite you to this conversation, and I'm very excited to have this conversation for next couple of weeks or months. Like in that way, like we are going to have this conversation as much as possible because I'm going to enjoy it in my end because before each and every lecture, I'm going to do some work. I'm going to uh, think about like how should I present. I mean, even though I'm working on dynamical systems, this approach to differential equations, I mean, this is a course that we don't usually have in this approach. So that is why it's going to be a fresh experience for me too. let's talk about a quick motivation. All right. So, take a quick, like, let's say a deep breath. The whole story of the introduction is now over. Now let's talk about, right, what we are gonna do. I briefly mentioned this also already, but let me tell you again. Let me give you the motivation in a totally irrelevant way, which means, like, let's say, usually in a differential equation course, we are going to find solutions, right? Uh, for a given differential equation, we are trying to produce a analytical solution or analytic solution or a numerical solution, something, right? So you have seen this already in different levels. So without talking about differential equations, let's talk about this. If I ask you to solve, this is kind of like a joke. You can all laugh, right? Of course, this is quadratic, right? Everybody knows what's happening here, right? So, uh, yeah, I can ask this question. Or I can ask like, oh, let's do something further. A cubic equation. Or I can extend this to the the fourth order. I just make it up. Some of them could be solved easily, some of them could not. Like, I didn't even check. I didn't even bother like thinking about solutions of these equations. But look at this. The story of, like, these are not differential equations, these are algebraic equations, right? So story behind algebra, if you think about that for a moment, was to work with these equations. If you go ahead and check like the history of algebra, the way that it worked was like to, challenging the renowned mathematicians one another, like saying, oh, can you solve this kind of like a cubic equation? Do you have a formula for that? I'm going to challenge you with this equation. Can you provide me the solution? That was the story. But then people kept thinking, okay, can we do that for any order, right? The fifth order, fifth degree. This is quadratic, cubic, and all right. So all of these orders, right? For each one, you can find like there are formulas. One can provide a formula for the quadratic, everybody knows. Cubic, there is a formula. For the fourth degree, there's a formula which is extremely complicated. Nobody is going to even have them in their mind, right? So the third degree and the fourth degree, we are not going to do that. We're not going to memorize them. We do not have that kind of a capacity in our brains. Some may. I most definitely, I do not. So if you think about the fifth degree, right, one can say like, oh, I'm going to try creating this formula. But if you know the story, what I'm going to talk about a little bit, like as an irrelevant entry point, starting from the fifth degree onwards, there is no formula, general formula that you can provide. So this is this method, the solution by formulas is basically like you're trying to take the roots, right? You're trying to do the radical, right? Solution by radicals is not a possibility from degree 5 onwards. If you know what I'm talking about, this is exactly what you have seen or what you're going to see in your uh, abstract algebra sequence when it comes to Galois theory, right? So this genius way of thinking about this story, right, with the contributions of Abel and Évariste Galois, right? So they did not try to answer this one equation at a time. No, they try to see the abstract playground behind this, which opened up many other subdirections like group theory, ring theory, and field theory, and then the whole section of like Galois theory. Like the whole entire story is going in that abstract layer, abstract playground, right? So that abstract playground is exactly where they are going to say, like, starting from the fifth degree, there is no hope of having a formula. You can individually work with some possible equations, polynomial equations for higher degrees, but it's not going to work for all cases. Now, why did I talk about this completely irrelevant approach to get to this story? Because what we do in differential equations in most cases, when we introduce them by, like, let's say like this, solve a differential equation. Let me write down a differential equation. So prime, we all know what prime means, right? In the previous case, when we considered those equations, we know, like, we are trying to find a solution for that x, right? A specific value for x. In this case, all right, what is your x? What are you going to find? One can say, oh, it's a solution. Oh, what do you mean by a solution? So if you give it a little bit of a thought, one can say, oh, it's a function. It's going to be a function that would balance this equation. All right. If it's a function, where does that live, right? What is the domain? Can you say something about it, right? So there are many formalities that you need to have behind this equation. And yet we can just hand wave and say, like, oh, we are going to solve this equation. So we can extend this idea to, like, let's say you can again say, uh, write down a different equation, right? Increase the order, bring any fancy terms into this, like this, oh, that, right? So solving these equations, it's just the same story. If we hand wave and if we say, like, if we just mute these technicalities, what we are going to do is, like, to blindly find solutions, some functions that would balance this equation. At a certain point, that might work. At a certain point, it might not. So when it doesn't work, right? So the point is this is just like dancing, right? So dancing without having a flow. Now, if you prepare the abstract layout, in this case, what is the abstraction? What is behind? Where are these all entities living in? If we can, if we do have that conversation at the beginning, then it is going to provide us more, not just a solution. Even if we do not have a solution, it might provide us a better intuition why it does not. What is happening here, right? That is exactly what we are going to do in this, right? So this abstract layout is exactly, this is the dance flow. That is your dance flow, where this is just the dancing without having, like, any target, right? So you can just you can dance, right? I mean, if one gets high with some alcohol, the I mean, they naturally define dance moves, right? So just like that. But it could be, uh, it can be done by many, but preparing that dance flow should be done carefully. You cannot do it while you're high in alcohol, right? So you need to do it with some care. So that's exactly what we're trying to build here. And of course, that's good. That's not going to be just abstract. Later on, that abstraction can be converted to an application or oriented, I mean, applications as well. Because it's heading towards dynamical systems where you can have, like, a whole bunch of applications in front of you. So the focus is going to be abstract. However, it's going to it's going to be fun. That's what I wanted to say in simple words. All right. So that is exactly the introduction, the beginning of the story. Um, I'm just thinking, should we just think about like let's say the approach, the starting step. I guess like we can in fact let's have a little bit of yes, little introduction or like how we are going to do this. Now let me tell you how I prepared this part of the lesson. To prepare this part of the lesson, I went ahead with the first edition of Arnold's book, where it's providing, I mean, like where it's provided, this matter is provided just like in the abstract form with no much information around. So I started in that. And then, of course, we may need more information. So for this basic setup, we are going to have like two different levels of the conversation. First of all, let's try to do it. Let's try to identify what we're trying to do. And let's try to do it in any ways. Like if no perfection guaranteed, let's try to do. And then once you go through that process, later, when we revisit the same topic, we are trying to have the formalities, we are trying to add it like the precise structure. So to begin with this entire story, right? The basic setup. These are what are the essentials that we need to have. We need to have uh, a set, right? Uh, Now, according to Arnold at the very beginning, the way that this is mentioned is like let M be an arbitrary. Oh, my handwriting is horrible. Arbitrary, arbitrary set. That is what it is mentioned, right? So it says like at least Arnold mentions like it's an arbitrary set. Now, this is an alarming point, everybody. So when we say arbitrary, there's something sloppy going behind that, right? So there is, I mean, you cannot say just arbitrary because especially when it's a set, it could be a set of cats and dogs, right? It cannot work in that way. So there should be some structure. So eventually we need to introduce this structure, but at least like with little contrast, I'm going to have little more addition saying, let's call it a non-empty at least. So if it is an empty set, there are no elements. So whatever the dynamics that you're going to define on this set, there is no dynamics because it's it's a it's void. Now, what we are going to do is this. All right, so let's pretend at least at this point, like arbitrary non-empty set, we have something. It could be anything. And when we have it, right, and then we are going to have also let T be a subset of R. Now, when we say T, all right, so when we introduce these symbols, of course, these do not need to give any intuition, but T maybe at a certain point we may see some intuition, but I'm not going to say anything, right? So it's any subset of R, any subset. Again, I'm saying that means that is also a little bit tricky. And then consider a collection. Collection of maps, right? I'm going to introduce these maps like this. G superscript T, this superscript is going to identify what function what mapping I'm talking about, and this mapping Meaning of a mapping is like basically like you map from that set to itself. So in other words, these mappings are going to be, in fact, right. So we do have this, right. So arbitrary mappings in this scenario, right? So if we consider collection of maps, let's say, and we will indicate that mapping the set of maps and the collection of maps. Let me indicate it by like a fancy F symbol, right? So in other words, what I'm saying is this F is none other than a family of these family, or like the collection of these maps. So I do have G superscript T from M to M, and such that, I mean, for all T in R. Or in particular, in this case, like, okay, let's consider like T in T, because that is the set that we considered, right? Here, there are many things that we need to introduce into this structure yet. I'm going to say here it is to say this is the mapping or the collection of functions that we are considering, and right, maps such that let's give a little bit of like some specialty. I mean, this could be any mapping, any collection. Other than saying it like arbitrary, I'm going to say this collection of maps is gonna have this special property, G of T plus S. So if you consider the superscript or the index of that function, I mean T plus S, that should be G of T times G of S. Now, when you consider this one, you have to be very careful, because now this is going to demand a little bit of more out of this set T. One cannot say like, oh, it is just a, we can always do this, right? Because one can say like, oh, T and S both are coming from this collection, and then when we consider T plus S, T plus S is going to be again like, oh, if it is living in this T, then there will be a function like this. Otherwise, there is no function like that. There is no mapping like that. So at this point, one can say, oh, this arbitrary subset is not enough. We need to say a little more. We need to give a little more structure. So that's exactly where one can say like, oh, let's try to make it like algebraically close. You can make it like a group, subgroup, or even without considering the subgroup structure, there are different ways of introducing this dynamical system. So what we are trying to do here is this, right? I'm trying to give you this sense where we have like all of these possibilities. If one is going to say like, oh, this is going to be, this T is going to be the collection of all integers from negative to positive infinity, like even including zero in the middle. So that is going to be an additive group, right? If you're familiar with the concept of groups from abstract algebra already, if you do not have that background, let's say simply it's going to be closed under two things. First of all, it's going to be closed under addition. Closed means like whenever you get two elements and when you add them, it's going to get into that same set. So it's not going to go out of that system, that set. And at the same time, if you get a number and if you make it negative, it's going to stay in that, right? So those are the two characteristics that I would like to have out of this set T. Now, one of these characteristics is evident right here. When we demand this property, it's going to give you just this scenario. However, at the same time, we need to understand, like, we need to have like two different ways of looking at it. One part is right. So in terms of that, whatever that closeness under addition, we are going to guarantee uh, at least the platform for this equation. And then what is really happening behind this equation? What are we trying to do with this? What you're trying to do is to make some kind of like a playground where we have consistency. So what you're trying to do is this. We are going to see this hopefully in the next couple of minutes. We are going to see this. What you're trying to do is to start with a point somewhere on that set M. Right? So let me draw a picture for this, and let's be hopeful that we are going to see that picture in mathematical form in a moment, right? So if you start from one point, like let's say you start from one point X and you apply this mapping, and you're going to jump to, like, let's say with G sub G super T, you're going to get to a certain point. Let me do this. Let's start with S. You're going to jump to a certain point, and then at that point, if you apply again, once again, like if you're going to measure T and you're going to apply GT to that. So you're going to get GSX here, and then you're going to apply again the second mapping, that's GT. Then you're going to get to a point. Now the action of this whole point is, it is like, even if you ignore this midpoint or the point that you found on the way, that stop that you had in the middle, even if you ignore that, you're going to have this directly from here to there. If you just directly measure that and apply GS plus T, what's happening is basically we make it consistent. If it is kind of like a trajectory, it doesn't really matter if you just stop at a certain point, and if you start moving again, you're going to have the same journey even if you stopped or not. So that is kind of like a trajectory that we are trying to plan here. That is a geometry that we are going to have out of this wonderful property. So in any ways, that property was pretty abstract, right? So it is just like, yeah, one can say, all right, second observation. One can say like, oh, this seems like some kind of an exponential form, right? One can say like that, but it is not, in fact, just the exponential property. It is much more general. I mean, it is not an exponent. It is not an exponent. Do not mix it up, because the same thing would work if you consider it in the subscript notation. I mean, it is just a symbol. It's a continuation, or it is the consistency of like the trajectories. So, by the way, hold on. I didn't say what I mean by this dot, right? That dot is none other than the composition, right? I should have mentioned that very carefully. Do you see, like when you try to prepare the abstract background, we need to work through that a couple of times, right? So this is exactly the composition you compose, right? This product structure that you're going to see is just that composition. So this is going to give us a very nice setup, right? So now, without making it too wide, let's narrow it down. Now, the setup. Let's revisit the setup. We talked about like the general setup that we are going to, or the setup that we are working on in this case. Other than considering any arbitrary time set or time set. Oh, I gave you the word, right? Don't say it loud. It is not just, I mean, it is playing as a time set. But what we are trying to do is to get this structure, since we are heading towards ordinary differential equations, other than considering set t, I'm going to say like our structure is like this. Consider this. Consider this combination. I mean, one can say it like as a set, but other than making a set, I will make it an ordered um, combination. I do have T, set of T, but in this case, I will consider the entire collection of R. This is our choice of T. From this point onwards, T. So T is being played by the real number, the entire real number line. So simply, our time set is going to be R. And then where these points are jumping here and there or moving smoothly would be a certain set called M, which is an unempty set. We just generically defined that right at the beginning, and we said it's an arbitrary set, which is kind of like too generic. We still need to add more structure to that. We're going to do that one step at a time. And then the third one is exactly the collection of those functions, or this collection we know that is exactly the functions g from m to m, or mappings from m to m. um, let's say more about this, right? So this collection now here, let's try to make it more precise here. For every t in R, such that inside we are going to say this. Let's consider like T1, T2, right? But the same thing that was played by T and S early. When you have that, it's going to be T1 and then composed, or like you can simply indicate it by a dot. But what do we mean by the product of two functions? It's none other than the composition. So this is the family, and this family is called um, the I mean, these functions or these mappings are called transformations. Transformations. That is our starting step. It's not a question mark, it is just an exclamation. Transformations. And even if you consider like this in general setting, there is something called the group of transformation. If you consider any arbitrary non-empty set, and if you try to prepare this setup, you can do that. So here, this is what we are going to have as the first proposition. Actually, you can try to prove this proposition. Or if you feel like this abstraction is going a little too fast, like at this point, try to understand this story, because we will definitely revisit this entire story with like a different angle again, right? But what we need to understand is like the first step, proposition one. Let's have something out of this. What we can see is like, okay, so we do have like a certain product structure in this function, right? So among these functions. So what if we consider this family F together with this structure? Oh, for this case, let me do something without having this property. included in it. Let's try to have this set separately. Let's have the set separately and let's define this structure separately. It's going to make things much more clear. Define this, I mean, define, or like it satisfies, let's say, consider this set, and for all T1, T2, we do have as an additional condition, we do have, should not be M, it should be R, the time, right? We should have this set. And then the transformations, of course, the transformations are none other than these functions that we consider. Now, let's consider this set, the transformations, and together with this product structure. The product is none other than the composition. If you consider this, this is a commutative group. This is going to form a commutative group. Commutative group. And it has a special name, right? So it is called a one parameter group of transformations. Now, this is the starting step. We need to think about now, by any chance, if you're not familiar with, like, let's say groups, I recommend you to take a look at the definition, because you are already familiar with the abstraction, right? So if you have not seen this, there are like only 4 points that you need to show: the closure, associativity, and the existence of an identity, and existence of the inverse for any given element, right? So this story, this whole thing is exactly giving us some structure called a group. But this is exactly where I'm going to say this uh, as a result. But then we will revisit. We should think about, like, let's try to work with this, right? In terms of like a particular proof, and we need to have that. We should have that conversation, and then maybe like as a less um, demanding structure, one is going to say something like this: proposition number 2. So some of these propositions, I mean, the way that you're going to prepare these propositions is like you're trying to make this abstraction, right? So when you try to do this, what you're doing is basically, when you feel something is going to like a certain property that seems like that's appealing, you're going to just write it down, you're going to craft it carefully, and then if you can see exactly that's true, right, then you're trying to make it a proposition, you're trying to make it a result, you're going to write down a proof. So this is one of the properties that I'm going to see in this case. Every mapping in F is 1 to 1. This is not the best way of writing it, right? 1 to 1. We know what 1 to 1 means. We know that uh, in basic algebra and set theory, right? So, and at the same time, you have the background from real analysis, so you know what 1 to 1 mapping is. Now, why this works? I mean, other than doing too much here, like I'm trying to introduce this the basic layer of this collection, right? So the basic background here, we introduce this formal setup where we have a time set and an unempty set and a family of mappings from that set M to itself. Together with that specific structure that would maintain like the trajectories, and that is what we had right here. So this is exactly this property, and with that, this is what you're going to get. We're going to get two components. One part is like the structure is going to be a group. That means you're allowed to do algebra on this. There's an algebraic structure on this among these mappings. You can play with that. And then the second one is every mapping, if you consider any mapping, it's going to be one-to-one, and it is like, I guess like we should have mentioned that earlier as a condition, but I mean, we did not have it as a condition, and we do have it right here. Now, what I'm saying is this. Mm, let's see. Let's try to see why this proposition 2 works. If we can get some kind of an idea for that, maybe like we can work around like proposition number 1, 2. I mean, of course, you can work with that as an example. Let's see. Let's try to have the outline of the proof. Let's try to prepare, like, let's try to see like, okay, of course, what is a one-to-one mapping? One-to-one simply means like if you have two different origins at the beginning, they should produce two different outcomes. They cannot produce the same outcome if you start with x1 and x2. They cannot provide the same value, right? When you map it, it should be like different f of x1, different, I mean, different g of x1, different g of x2, something like that. But the way that we're going to establish this fact is like uh, exactly the contrapositive, right? Other than saying like g1 is not equal to, right, let's say the general definition for one-to-one is right this, right? x1 not equal to x2 should imply whatever the function. I'm not going to use f here to confuse it with the family. I'm going to say g, right? Just say gx1 should not equal with gx2. But look at this. In mathematics, like when we work with like things, when we work with uh, mathematical entities, working with equations or inequalities, it's easy. But when you work with non-equalities, right? When something is not equal to the other, right? It could be the whole lot of spectrum. So if you start from this end, it's pretty hard to do something, right? So this is exactly why, if you have seen the other way, the contrapositive behind this statement, I mean, the contrapositive is none other than a way to work around this, right? So this, right? So for the entire domain, right? For every x1 and x2, x1 not equal to x2 would imply gx1 not equal to gx2 is going to be if and only if the contrapositive gx1 equals gx2. By any chance, if they started with I mean, if they end up with the same value, they must start with the same value in the domain. So this is the contrapositive, but look at this. Here we are playing with equalities. When you have an equality, there are things that you can write down about it, but the inequalities, like not inequalities, non-equalities, like it's not the equality. When you just contrast the equality, then there is a confusion, right? A confusion, or less things that you can write, less things that you can present. So this indirect approach is really helpful in that way. So let's look at this. This is what we need to prove. But look at this. Let's pick a function in this. So since we have this background, let me just get rid of this. And let's say let x1, x2 be on this um, collection. And even before doing that, what are we trying to establish? We are trying to establish a certain, or like let's say selected, or any given mapping in the collection of F is going to be 1 to 1. So let's start with that. Let G T GT, right? We know the form of this, right? It's going to be a G together with it's called by that structure, or the index. So let GT be one of the elements of not M, the collection of transformations. Yeah. And then I'm going to consider like x1 equals x1 and x2 from that collection. And let's assume, suppose that gx1, gx2. What we need to establish is this. What we need is, we need to show that x1 equals x2. Now, starting from this statement, what we need to establish is x1 equals x2. How can you do that? Now, this is where we need to get a little bit of an idea about like the structure here, right? If you compose minus t, right? Don't forget, this is valid for all values, right? Therefore, you can just do this. If you do that, what can you say in the next step? And then by the assumption that we made related to this product structure, right? We know this is none other than g of -2 plus -t plus t and x1. And then this will end up getting g0 x1. What is this g0? This is going to be exactly like the structure. Now, if you try to think about this the action of this mapping, what we indicate by G0 is none other than the identity mapping in this. What is the identity map? It maps to itself. Now let's try to think about, like, let's say if this T is playing the role of time, what it does is this. You start from a certain value, let's call it x1, and if you apply gt into that, right? In this scenario, what you're seeing is like, let's say, after time t, where it should be. You're trying to get that value, right? So what it says is like, you start from two different points and you end up in the same time, you will end up somewhere the same point. If that happens, what we are saying is it should have started with the same origin. So if you start from one single, if you're at a certain point, the simple story is you can look at what happened in the past along the trajectory, and you can recognize where you started it from, and you can identify it uniquely. And what this gives us is x1 equals x2. The simple fact is g0 is none other than the identity function. ID simply means the identity. Identity of what? If you go back and check now, proposition number one, I told you it is already a group structure. For a group structure, there should be there should be one mapping in this collection which acts as a group identity. Who's that group identity? That is none other than the identity function, and that is exactly what's playing this role. So this tells us this function is going to be, I mean, this mapping is going to be one-to-one. So now look at this. We simply, now what we did was this. We didn't do much except for introducing this. First of all, we introduced like exactly the cause, and then we had like right away, without having any computational example, we just immediately jumped into this abstract form of the story and we started proving stuff. And this is exactly what I wanted to point out. Now, in the next session, this is what we are going to do. So consider this whole thing. I mean, any ambiguities that you might have had, like you are having right now with this endpoint. Wait a minute. How did we get here, like with this abstraction? How many things, like when we say like the set M arbitrary set, what do we mean by that? So all of these, I mean, if we feel that there are missing points behind this and we need to make it more formal and smooth as a conversation, from that level all the way down to like what we're trying to describe, like, do we see any differential equations here? Not yet, right? Do we see any background for differential equations? Not yet. So preparing that background is exactly what we are going to do in this conversation. So my plan for the next lesson, I mean, for this lesson, right after the introduction of the course, I wanted to give you like a direct uh, structure, what we are, the way that we are going to do it. This is just a test. And then in the next lesson, what we're going to do is in the next lecture, we are going to have like, let's say, according to the imperfect approach, or where we need to have little more details added into, provided by Arnold's first edition, we are going to have that conversation. We're going to make it as much as possible. We will try to find where it's lacking more information, where it needs to be supplemented. And then that's exactly what we're trying to do with edition 3, or like the way that we are going to do it. Like, it need not to be just the textbook. It should be our intuition, the way that we are going to prepare uh, our understanding on our notes and our um, in our work, in our presentation. So that's exactly what we're trying to work on the second uh, lecture onwards. All right, so in that way, we are going to have this introduction and overview for 2, 3 sessions that would be natural in this scenario, and then we will get to the relevant layer of conversation where we are going to have, I mean, gradually we will progress to the next levels. All right, so with that, I'm going to conclude this session and I will see you in the next lesson. So take a moment to skim through Arnold's book, but my recommendation when it comes to certain types of solutions, like especially in edition number 3, if you feel like certain components, I mean, solution oriented conversations, do not worry too much about it, because we are not planning to do that in our work. And then on the other hand, if you're looking at edition number 1, uh, if you get confused by the whole abstract conversation, do not overthink, because that's exactly what you're going to elaborate in upcoming lessons. All right, I'll see you next time. Have a wonderful week, and let's meet the next session.